Good day everyone! I'm Leslie May Bognot and I will be presenting the Luis Amor figure. So here is how it looks like. For the front, containing the elements L, U, I, and S, and for the back, A, M, O, and R. The moves are the following. For L, do nothing. For U, rotate 90 degrees counterclockwise. For I, rotate 180 degrees counterclockwise. For S, rotate 270 degrees counterclockwise. For A, flip vertically. For M, rotate about the right diagonal. For O, flip horizontally. And for R, rotate about the left diagonal. And now let's try involving the operation star. For example, we have L star U. So we have first is L, do nothing, which makes the figure stays the same or look like this. Then we may now proceed to the second move, which is U, or which is to rotate 90 degrees counterclockwise. And we will now have this figure. So here is how it looks like. For L star U, we have this kind of figure. And then after knowing the result, we may now put it in the table. So here is the table of results. So for L star U, the result is U. Next, we try I star S by going back to the moves and clicking I first, which makes the figure rotated to 180 degrees counterclockwise, resulting to this figure. And after which, we may now proceed to the next move S, which is to rotate the figure 270 degrees counterclockwise, resulting to U, containing the elements U, I, S, and L. So this means that the move shown in the slide after clicking the final move is the result of the operation star, which will be put now on the table of results. Therefore, I star S is equal to U. Another is A star I. So first, let's flip the figure vertically, resulting to A, containing the elements A, M, O, and R, then rotating the figure 180 degrees counterclockwise, resulting to O, and put it in the table. Therefore, A star I is equal to O. And by continuing the process, we arrive at these results as shown in the table under Operation Star. But the question is it a group? Let's find out by identifying its properties. So first is the test of associativity, which can be checked by inverting the table and having the same elements for every row and column. In this slide, the original and inverted table are shown, which at first glance doesn't look the same. But the good thing is, we may interchange rows and columns. As we can notice, columns S and U must be interchanged to look like the original table. Since the inverted table is still not the same with the original one, we notice that columns O and A must also be interchanged, arriving to this table. And by comparing the inverted table whose columns were interchanged with the original table, we now arrived at similar table, which means that the group is associative. Therefore, property 1 is satisfied. We now proceed to the next property, which is the identity element, which must be obtained in a group. To identify the identity element, we look for the row and column similar to LUIS, AMO, and R, which appears to be located on the first column and first row as well. Then, the identity element will be where the intersection of the certain row and column, which appears to be L. Therefore, there exists an identity element which is L. We now proceed to the third property, which is identifying the inverse elements. First, we need to look at the identity element for every row and column. Then we may already identify the inverse. For the first one, we may say that the inverse of L is L. The inverse of U is S. The inverse of I is I. The inverse of S is U. The inverse of A is A. The inverse of M is M. The inverse of O is O. And lastly, the inverse of R is R. So this means that an inverse exists for every element which satisfies the third property. To sum it up, for the first property, is it associative? Yes. Next, is there an identity element? Yes. And lastly, does every element have its inverse? Yes. So therefore, it is a group. If it is a group, then it must have subgroups. Now let's see. Starting from subgroups of order 2, since the subgroup of order 1 is the identity element. L star U equals U, U star U equals I, and I is not an element of L star U. Therefore, it is not a subgroup. Next, L star I equals I star I is equal to L, and L is an element of L star I. Therefore, it is a subgroup. Another, L star S is equal to S star S is equal to I, and I is not an element of L star S. Therefore, it is not a subgroup. Next is L star A, which is equal to A. Then A star A is equal to L, and L is an element of L star A. Therefore, it is a subgroup. Next, L star M is equal to M star M is equal to L, and L is an element of L star M. Therefore, it is also a subgroup. Then, L star O is equal to O star O is equal to L, and L is an element of L star O. Therefore, it is a subgroup as well. Another, L star R is equal to R, then R star R is equal to L, and L is an element of L star R. Therefore, it is a subgroup. So the following are the subgroups. Next is to classify the subgroups into improper, proper, and trivial subgroup. So for the improper subgroup, it contains L is equal to LUIS, AMO, and R, and star. Next, for the proper subgroup, we have for L2 equals LUIS star, L3 equals LIAO star, L4 equals LIMR star, L5 equals LI star, L6 equals LA star, L7 equals LM star, L8 equals LO star, and L9 equals LR star. And now for the trivial subgroup, which is also the identity element, we have L10 equals L star. After identifying the subgroups, we may now have a lattice diagram which is now presented showing the different subgroups that we discovered. So aside from being a group, is it also a cyclic group? Let's try to find generators starting from U star U equals I star U equals S star U equals L, and L star U equals U. This means that the generator of the group LUIS is U, as it generates it. Next, I star I equals L, and L star I equals I. This means that the generator of the group Li is I. Another, S star S equals I star S equals U, and U star S equals L, and L star S equals S. So this means that the generator of the group LUIS is S. So notice that U is also the generator of that group, which only means that there are two generators for such group. Next, A star A equals L and L star A equals A. M star M equals L and L star M equals M. O star O equals L and L star O equals L. And R star R equals L and L star R equals R. Therefore, the generators for each group are A, M, O, and R consecutively. So this shows that there is no generator for the group containing the elements L, U, I, S, A, M, O, and R. Therefore, the group is not cyclic. We now proceed to the cyclic subgroups. First, let's try LU. L star L is equal to L star U equals U star L equals U, and U star U equals I. And I is not an element of LU. Therefore, it is not a cyclic subgroup. Next, Li. L star L equals L star I equals I star L equals I, and I star I equals L. And L is an element of Li. Therefore, it is a cyclic subgroup. Next, Ls. L star L equals L star S equals S star L equals S, and S star S equals I. And I is not an element of Ls. Therefore, it is not a cyclic subgroup. Next, we have La. L star L equals L star A equals A star L equals A, and A star A equals L. And L is an element of La. Therefore, it is a cyclic subgroup. Another is Lm. L star L equals L star M equals M star L equals M, and M star M equals L. And L is an element of Lm. Therefore, it is a cyclic subgroup. Next is Lo. L star L equals L star M equals M star L equals M, and M star M equals L. And L is an element of Lo, therefore it is a cyclic subgroup as well. And lastly, Lr. L star L equals L star R equals R star L equals R, and R star R equals L. And L is an element of Lr, therefore it is a cyclic subgroup. So all with check marks are cyclic subgroups. We now proceed to the permutation. So let us first identify the elements in the given figure, which is also our original figure. So these elements are L, U, I, S, A, M, O, and R. And for our raw sub-zero, we have for the first and second row, we have L, U, I, S, A, M, O, and R. And raw here is represented by different rotations. So here is how the figure looks like when it is rotated 90 degrees counterclockwise. And now we have raw sub 1, which is equal for the first row. We have the original figure containing the elements L, U, I, S, A, M, O, and R. And for the second row, which is rotated 90 degrees counterclockwise, we have U, I, S, L, R, A, M, and O. And now, when the figure is rotated 180 degrees counterclockwise, the second row will contain the elements I, S, L, U, O, R, A, and M. And the first row will stay the same since it represents the original figure or the original elements. And this will now be our raw sub 2 since it is also a rotation. Next, when the figure is rotated 270 degrees counterclockwise, the second row will contain the elements S, L, U, I, M, O, R, and A, and that will be our raw sub 3. And for this slide, we will now be having the figure flipped. And for the first one, the figure is flipped vertically. And so we will have the elements for the second row Amorlui and S, and that will be our mu sub 1. So take note that mu is represented by different flips, and the rho is represented by rotations. And now, when the figure is flipped horizontally, the second row will contain the elements O, R, A, M, I, S, L, and U, and that will be our mu sub 2. Next, when the figure is flipped using the dotted line, it seems like it is flipped about the right diagonal. And therefore, we will be having the elements M, O, R, A, S, L, U, and I for the second row. And that will already be our mu sub 3. And lastly, when the figure is flipped using the dotted line, which seems to be flipped about the left diagonal, the second row will contain the elements R, A, M, O, U, I, S, and L, and that will already be our mu sub 4. Let us try permutation multiplication by having the original position, which is our rho sub 0 as our multiplier. Then rho sub 1 as our multiplicand, and in multiplying permutations, we need to look at the second row of the multiplicand first, and then look for its equivalent in the first row of the multiplier and getting the element corresponding to it. And that will already be our result or answer or product. So for this one, we have U, and look for it in the first row, and then corresponding element to it is U. Same with I, so look for it here, and the answer is also I. And after continuous process, we will be arriving at this result. And notice that the result is equivalent or similar to the rho sub 1, since we are multiplying the permutation by the original position, or which is also, or which seemed to be the identity. And therefore, the answer will always be the multiplicand, especially if it is the multiplier, and vice versa as well. And therefore, our answer for the following is also the multiplicand. So what if we try rho sub 1 as our multiplier and rho sub 1 up to mu sub 4 as our multiplicand? So let us focus first on the first one. We have U here, and then look for it in the first row of our multiplier, and then the corresponding element is I. So that will be our first element. Next is I, then I, S. So the second one is the second one is S. So the first two elements are IS, then S, S, L, then L, L, U. So the first four elements are I, S, L, U already. Then next is R, R, O, then A, R, M, M, A, then O, O, M. Therefore, the result when rho sub 1 is multiplied to itself is this one. So notice that the result is similar or is equivalent to this one, which is the rho sub 2. Therefore, the answer here is rho sub 2. And by continuing the process, we will arrive at these results. And by continuous process, if we have rho sub 2 as our multiplier, we have these results. Same with rho sub 3 as multiplier, we have these results. Next is mu sub 1, we have these results. Then mu sub 2, we have these results. Then mu sub 3 as multiplier, we have these results. And lastly, mu sub 4 as multiplier, we have these results. And after a series of computations and processes, we arrive at this table of results. And now we may already be able to identify its subgroups. So for the first one, we have A equals rho sub 0, rho sub 1, rho sub 2, and rho sub 3. For B equals rho sub 0, rho sub 2, mu sub 1, and mu sub 2. For letter C equals rho sub 0, rho sub 2, mu sub 3, and mu sub 4. D equals rho sub 0 and rho sub 2. E equals rho sub 0 and mu sub 1. F equals rho sub 0 and mu sub 2. And G equals rho sub 0 and mu sub 3. And lastly, H equals rho sub 0 and mu sub 4. And for the trivial group or the trivial subgroup that we are referring in the previous slides, I equals rho sub 0, which represents the identity element as well. And of course, we may now be able to construct a lattice diagram for the said group. And this is how it looks like. So that's all for my presentation. Thank you for listening. Good day and God bless. And for more questions, you may email me at bagnotlesliemay@gmail.com.